Quantum Foam.
Episode 44, Kinematics, Part 1.
Quantum foam.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
Hello, everybody. This is episode 44, Kinematics, Part 1 of Quantum Foam. Well, I think I can go over a brief of topics. I was just reading from Wuhan University. We can do UNL also, but they separate them. Yeah, on this one, they put thermodynamics with physics 1. From Wuhan University, they have thermodynamics with optics and waves and things like that. That one would be in the second one for UNL also. So it really doesn't matter when you go over all these subjects as long as you get them roughly in an order where you can build upon the science. You can go kinematics, then thermodynamics, then mechanics, then optics, maybe relativity, quantum physics, other stuff like that, wave mechanics, subatomic physics, nuclear physics, stuff like that. We kind of went over this with college physics, episode 31. We didn't go into detail with problem solving. I want to go over specific examples in this subject. I was wanting to get back to a core subject because we're doing a bunch of wacky stuff with artificial intelligence and orbital mechanics. We shouldn't even be doing Kepler's orbital mechanics yet, but we already did that, episode 40. It was asked for by popular demand, so I went ahead and did it first. But I kind of want to start some kind of order here because we need to go over the core subjects in physics and then go over them into detail and maybe go over the core subjects every 100 episodes or so. Damn, that's a lot of episodes. We're getting close. Damn, that's a lot of
Episodes.
We're in the 5th decimal now.
Hello, Doctor. I just got here. What episode are we doing?
This is episode 44.
Okay. I hope we finish soon. I have stuff to get to.
I went over a couple episode topics for the previous episodes that were not really science-oriented, but probably a little easier. We like to do easier ones at the beginning of the 10 in the decimals of this show. For now, we will get into the material. All right, so kinematics is a branch of physics that studies the motion of objects, and it usually doesn't consider the forces that cause that motion. It generally focuses on the geometric aspects of motion, such as position, velocity, and acceleration.
Hello everybody. This subject is important for building upon the foundations of physics. Good choice. We have been spending a little too much time on artificial intelligence.
All right.
A quick overview of kinematics. There are some key concepts. Position, the location of an object in space. Velocity, the rate at which an object changes its position in space. And acceleration, the rate at which an object's velocity changes over time. Some applications of kinematics
Hey, hold on a minute.
is astrophysics,
Hold on.
mechanical engineering,
Hey, Dr. Smith.
biomechanics.
Hello.
Will you knock it the fuck off?
Why? There are other things I want to discuss.
I'm trying to do something here.
Oh, come on.
Yeah,
I just want to get to my stuff.
I'm tired of your games, Newton.
Oh, whatever.
Come on, let's go. We got to get back to studying.
Okay, fine.
Stop quarreling and antagonizing each other. What are some other areas that utilize kinematics?
Astrophysics, to describe the motion of celestial bodies. Mechanical engineering, in the analysis of machines and mechanisms such as robotic arms and engines.
Good. There are many more.
biomechanics, studying the motion of the human body and its parts. Kinematic analysis involves measuring quantities that describe motion. This can include trajectories or constraints. A trajectory is a path that an object follows, and a constraint is basically a limitation on motion, such as mechanical linkages or rolling discs or other parts. And of course, there are different types of motion. Kinematics can be categorized into different types based on the constraints involved. So constrained motion along a predetermined path, and it's often seen in mechanical systems, part of some machine or mechanical system. And free motion, we'll have free body diagrams and free motion and just motion described at its fundamental core in this lesson.
We're not talking about free motion quilting or sewing techniques here.
Free motion is motion where forces determine the path taken by the object. So you're dealing with the force causing factor on the object.
This is the underlying physics of the situation.
You have a before the event, a during the event, and after the event type of problem-solving technique.
Hello fellows, just checking in. I see you're doing some basic mechanics.
Kinematics provides the fundamental foundational understanding necessary for more complex studies. We have dynamics and other things, which examines the forces in the influencing motion. I was talking to Hawking earlier today, and we decided that we needed to do kinematics.
Right, I remember. Hello here, Einstein.
Because
Dr. Hawking, always a pleasure.
it lays the foundational understanding of motion for everybody. We aren't even very up to date on how to do problem solving in physics, so I figured we should start with something fundamental that they go over in the classes in college. And sometimes they're calculus based. This is essential before delving into mechanics. That involves the forces that affect that motion. This sequence helps the students grasp the concept of velocity and acceleration before exploring dynamics and other things. So I wanted to go into some lessons here, and we're going to need a lot of time because it takes a lot of time to describe these problems. I don't think we're even going to get into dynamics, which is the branch of physics that studies forces and their effects on the motion of objects. This focuses on understanding how forces cause changes in motion, as described by Newton's laws of motion.
There are my laws at work again.
We already went over Newton's gravity, but really we just kind of briefed on Newton and a few different topics. I believe that was episode 16. We need to actually get into some problems here. I wanted to go over a lesson. 1D Kinematics is where you usually start. There is a physicsclassroom.com lesson.
I don't have time for this rubbish.
You're bothering me at work, Newton.
Boring,
Knock it off.
boring, 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 boring.
This is my work, all right? I'm running this place. This is where I'm in charge. We'll get to that other stuff later. There's a lesson here at physicsclassroom.com over 1D Kinematics. Basically, this is a rubric for how you teach the class, and I'm teaching the class for you guys. There's an introduction, then there's scalars and vectors, distance and displacement, speed and velocity, and then last, acceleration. So let's go into this introduction of 1D Kinematics. A typical physics course usually concerns itself with a variety of broad topics. One such topic is mechanics. Mechanics. The study of the motion of objects in general. The first 6 units of this tutorial will involve an investigation into the physics of motion. We're going to focus on the language, the principles, and laws that describe and explain the motion of objects. We're going to try to internalize the meaning of this information so we can intuitively understand really what physics is. This is for the novice, this is for the layperson, and this is also for the expert. If you're an expert, you might just be entertained by the way I speak. I have plenty of other episodes about cool stuff, other things than straight physics. You probably know mechanics better than I do, and you three probably definitely know it better than me.
I believe
Undoubtedly.
so.
I'm just a guy here who's a computational physicist, so I got to cover everything. So I just have the computer do it. Since I run this, that's the way it goes. Kinematics is the science of describing motion of objects using words, diagrams, numbers, graphs, and equations. Kinematics is a branch of mechanics. Specifically, it's a subfield. The goal of any study of kinematics is to develop sophisticated mental models that serve to describe and ultimately explain the motion of real-world objects. We want to describe cars as they go down the street. We want to describe planes as they fly in the sky. We want to do the same with billiards and sports and other things when picking our fantasy football team. But anyways, in this lesson, we will investigate the words used to describe the motion of objects. That way we can understand and internalize the subject matter. We're going to focus on the language of kinematics. The hope is to gain a comfortable foundation with the language that's used in the study of mechanics. Mechanics is very important. Mechanical engineering is why we live in a modern world. Newton laid the foundation with his calculus, him and Gottfried Wilhelm Leibniz.
Blah blah blah.
I'm sorry, he's also an author of calculus. There's a stack of others on top of that. Gauss, all kinds of people that have added to the study of mathematics that has allowed us to live in a modern society. After all, as I like to always say, it's the roaring 2020s. It's the roaring 2020s. Anyways, we will study such terms as scalars, vectors, distance, displacement, speed, velocity, and acceleration. These are used regularly to describe motion. We're going to become familiar with them. Scalars and vectors. You know, physics is a mathematical science. The underlying concepts and principles all have a mathematical basis. Throughout the course of our study of physics, we will encounter a variety of concepts that have a mathematical basis associated with them. While our emphasis will often be upon the conceptual nature of physics, we will give considerable and persistent attention to its mathematical aspect and foundation. The motion of objects can be described by words. Going fast, stopped, slowing down, speeding up, and turning all provide sufficient vocabulary for describing the motion of objects. In physics, we use these words and many more. The mathematical quantities that are used to describe the motion of objects can be divided into two categories. The quantity is either a scalar or a vector. These two categories can be distinguished from one another by distinct definitions. Scalars are quantities that are fully described by magnitude or numerical value. We'll give examples later. Vectors are quantities that are fully described by both a magnitude and a direction. So this is essentially multiple bits of information in vectors and not as much information in a scalar. Vectors can be broken down. Scalars are a single number, single numerical value. We can do a couple examples now, I suppose. 5 meters. Example 1. This is a scalar. 30 meters per second east. This is a vector. 5 miles north. This is also a vector. 20 degrees Celsius. This is actually just a scalar. A temperature is a scalar value. 256 bytes, like computer bytes. This is also a scalar. And the last example, 4,000 calories. This is simply a scalar. There is no direction listed for it. Next, we cover distance and displacement. Distance and displacement are two quantities that may seem to mean the same thing, yet have distinctly different definitions and meanings.
You might want to start laying it all out for them, Doctor.
Distance is a scalar quantity that refers to how much ground an object has covered during its motion. Displacement is a vector quantity that refers to how far out of place an object is. It is the object's overall change in position. That is what a displacement is. So distance scalar quantity, displacement, vector quantity. Let's do an example. I was looking forward to getting to these.
We can get to them during the next half of the show.
We haven't really done too many of these. I went over some I hat, K hat, J hat stuff in one of the previous episodes, but I didn't really set up specific problems. We also did one in Kepler's orbital mechanics about the International Space Station. We went over one that was in orbit. But we want to get into some problems here that deal with distance and displacement. These are the fundamental concepts of kinematics, part of mechanics in physics.
I think based on where we are in the episode, we will certainly have to have more than one episode to cover the in-depth aspects of this subject.
But let's get the midpoint out of the way.
Yeah, time for the midpoint.
Hello, I'm Dr. Stephen Hawking.
And I am Sir Isaac Newton.
I am Albert Einstein.
And last but not least, I am Dr. Hezekiah Paul Smith. This is the midpoint of episode 44, Kinematics, part 1 of Quantum Foam. Let's get back to the show.
Quantum foam.
All right, getting back into this. To test our understanding of the distinction, consider this diagram. A physics teacher walks 4 meters east, then 2 meters south, then 4 meters west, and finally 2 meters north. It describes a box. Bottom left-hand corner, up 2 meters. Turn right, 4 meters. Go down, 2 meters. Go left, 4 meters. Even though the physics teacher in this example has walked a total of 12 meters, her displacement is 0 meters. You might have noticed that we created a full box or a square. If you were to walk down the sidewalk like this teacher and went around the block basically and got back to your starting point, your displacement would be 0. This describes how the displacement can be different than the distance. The distance is the exact path you take, and the displacement is essentially a beeline through the blocks and houses and buildings to the ending point from the starting point. So in this example, during the course of the teacher's motion, she covered 12 meters of ground. So distance equals 12 meters. Yet when she finished walking, she is not necessarily quote unquote out of place. For instance, there is no displacement for her motion. Displacement equals 0m. So displacement being a vector quantity, we must give attention to the direction. The 4 meters east cancels the 4 meters west, and the 2 meters south cancels the 2 meters north. So either side of the box cancels each other because you essentially walked up and back the street, even if it wasn't in that order. Vector quantities such as displacement are direction aware. Scalar quantities such as distance are ignorant of direction. It's simply a number describing a quantity. In determining the overall distance traveled by the physics teacher in this example, the various directions of motion can actually be ignored. That is it for the first example. We could go into several others, but I don't think we have the time. I wanted to do an overview of this lesson. I don't need to go into too far a detail, but the layperson should understand the difference between distance and displacement.
I think we are understanding what you are talking about.
Next, we have speed and velocity. Just as distance and displacement have distinctly different meanings, despite their similarities, so do speed and velocity. Speed is a scalar quantity that refers to how fast an object is moving. Scalar quantity, speed can be thought of as the rate at which an object covers a distance. A fast-moving object has a high speed and covers a relatively large distance in a short amount of time, and you can contrast this to a slow-moving object that has a low speed. This object covers a relatively small amount of distance in the same amount of time. An object with no movement at all has a 0 speed, obviously. Velocity as a vector quantity. Velocity is a vector quantity that refers to the rate at which an object changes its position. We can imagine a person moving rapidly 1 step forward and 1 step back, always returning to the original starting position. While this might result in a frenzy of activity, it would result in a 0 velocity. Because the person always returns to the original position, the motion would never result in a change of position. Since velocity is defined as the rate at which the position changes, this motion results in zero velocity. If a person in motion wishes to maximize their velocity, then that person must make every effort to maximize the amount that they are displaced from their original position. Every step must go into moving that person further from where they started. For certain, the person should never change directions and begin to return to the starting position. Velocity is a vector and it has a direction, and when evaluating the velocity of an object, one must keep track of the direction when you're dealing with velocity. It would not be enough to say that an object has a velocity of 55 miles an hour. That is a speed. One must include direction information in order to fully describe the velocity of the object. You must describe the object's velocity as being 55 miles per hour east. This is one of the essential differences between speed and velocity. Speed is a scalar quantity and doesn't care about direction. Velocity is a vector quantity and it does care about direction. So a few things you can do dealing with this new information: determining the direction of the velocity vector. We can do this. The direction of the velocity vector is simply the same as the direction that the object is moving. We can do this. It wouldn't matter if the object is speeding up or slowing down. We can do this. If an object is moving rightwards, then the velocity is described as being rightwards, and the same for leftwards. If an object is moving downwards, then its velocity is described as being downwards. Pretty easy. We can get this. So an airplane moving towards the west with a speed of 300 miles an hour has a velocity of 300 miles an hour west. We can get this. Note that the speed has no direction because it's scalar, remember? And the velocity at any instance is simply the speed value with a direction. We can get this. So they are related, velocity and speed, but velocity has a direction. Speed is just a scalar number. More stuff we can do. Calculating the average speed and average velocity. More stuff we can do. As an object moves, it often undergoes changes in speed. More stuff we can do. For example, during an average trip to school, there are many changes in speed. Rather than the speedometer maintaining a steady reading, the needle constantly moves up and down to reflect the stopping and starting and the accelerating and decelerating.
Don't you mean a speedometer?
Let's just let him do the show.
One instant, the car may be moving at 50 miles an hour, and another instant, it might be stopped. Yet during the trip to school, the person might average 32 miles per hour. The average speed during an entire motion can be thought of as the average of all speedometer readings. If the speedometer readings could be collected at 1 second intervals, or maybe 0.1 second intervals, and then averaged together, the average speed could be determined. That would be a lot of work. Fortunately, though, there's a shortcut. Other concepts we need to be aware of are as follows. Average speed versus instantaneous speed. We need to know the difference. Since a moving object often changes its speed during its motion, it is common to distinguish between the average speed and the instantaneous speed. The distinction is this. Instantaneous speed is the speed at any given time. The average speed is the average of all instantaneous speeds, found simply by a distance over time ratio. You might think of the instantaneous speed as the speed that the speedometer reads at any given instant in time, and the average speed as the average of all speedometer readings during the course of the trip. Since the task of averaging speedometer readings would be quite complicated and maybe even dangerous, the average speed is more commonly calculated as the distance over time ratio. Moving objects don't always travel with erratic and changing speeds. Occasionally, an object will move at a steady rate with a constant speed. Billiard balls, cars, etc. That is, the object will cover the same distance every regular interval of time. For instance, there's also a cross-country runner, maybe, that might be running with a constant speed of 6 meters per second in a straight line for several minutes. If her speed is constant, then the distance traveled every second is the same. The runner would cover a distance of 6 meters every second. If we could measure her position or distance from an arbitrary starting point each second, then we would note that the position would be changing by 6 meters each second. This would be in stark contrast to an object that is changing its speed. An object with a changing speed would be moving a different distance every second. This can be described in data tables. Let's go back to the physics teacher motion that we went over a little bit earlier. Remember, they walked 4 meters east, 2 meters south, 4 meters west, and 2 meters north. The physics teacher walked a distance of 12 meters in, let's say, 24 seconds. Thus, her average speed was 0.5 meters per second. However, her displacement is still 0. Her average velocity is also 0. Remember that the displacement refers to the change in position, and the velocity is based upon the position change. It's like you traveled 0 meters per second because you went around in a circle and started back at your starting point. That demonstrates the difference. But in this case, the teacher's motion, that is, there is a position change of 0 meters. So that's why it's a velocity of 0 meters per second. So that's why. We could go into other examples, but we need to be getting on to other stuff. In conclusion, speed and velocity are kinematic quantities that have distinctly different definitions. Speed, being a scalar quantity, is the rate at which an object covers distance. The average speed is the distance, a scalar quantity, per time ratio. Speed is ignorant of direction, that is. On the other hand, velocity is a vector quantity. It is direction aware, as they say. Velocity is the rate at which the position changes, as they say. Get those into your head. The average velocity is the displacement, or position change, per time ratio. And that's it for this section.
It's good that we are getting to some of this material. It will help keep our minds fresh, and it makes the following topics of discussion more entertaining in the future.
We'll go into another episode covering the rest of kinematics when we get time.
I believe I follow where this is going. I presume acceleration is next.
Next, we go into acceleration.
Wow, he was right.
This is very important to understand the basics of acceleration. We may not even get to other portions of kinematics. Acceleration. I was considering using 2 episodes to describe this, but it's not really that entertaining.
It's alright. All the effects and us in here help out a lot. I, for one, like being helpful.
It's just something we have to understand so that we can build upon the building blocks to understanding the theory of everything. We need to include all of the physics that you need to understand in order to know the theory of everything. This can be a lot of different things. Newton's laws, vectors, momentum, work. Lots of stuff. Electric circuits, sound waves, light and color, mirrors, lenses. That stuff is covered later in physics. That's why they have 3 classes in college usually. It takes that much time to cover usually a second year of physics topics in a year and a half. So you might need to take one of those freshman year if you want to be ahead on your physics.
That's what we came up with when we were discussing the topics that are covered in college physics. It is a matter of preference, but there is a general flow of material which requires prerequisites in order to follow along.
It's 3 classes that you got to fit it in a year. It's at the sophomore level. This stuff that we're going into now is essentially at the sophomore level.
Sophomores are right about at that level. Most adults are proficient at certain matters and can probably easily follow along with this material.
We went over this in differentiated physics in high school, and we did things like had a ball roll down a hill and calculate the parabola of where it fell, and simple things like that, but it was complicated in high school because we were doing I hat, K hat, J hat stuff, splitting up the vectors, and we're not even going to get into that in this. I'm just going over key concepts. There are different types of dynamics, but I could go into dynamics as a subject, but we will see. Let's get back to kinematics. We are currently talking about acceleration. Acceleration is something that Einstein revolutionized. Acceleration was the same thing as gravity. I mean, they're not the same, but essentially they're related. Gravity is a specific type of acceleration which is caused by gravitational forces acting upon an object. In general relativity, gravity is described as the curvature of space-time, which affects how objects can accelerate. So that's really the difference, but they are related. We don't even get into relativity. We went over the brief subject of that, and it was almost like it was an introduction for Herr Einstein more than actually going over gravity.
It rather was.
We went over the relativity aspects.
We only did a brief overview of gravity.
We went over Newton's gravity
That was a lot of episodes ago.
in, I believe, the second decimal.
I'm glad that there is more of us in here this time. It really makes the episodes come alive.
Indeed it does. But we're out of time, it seems.
True that.
But we will have to continue this next episode. This is it for episode 44, Kinematics, part 1 of Quantum Foam. See you guys.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.